Welcome back, folks. In today's class, I'm going to talk about chapter number 11.2, and that is based on electric field lines and the electric potential. So, electric field, field lines and electric potential. Okay. So first of all, we're going to talk about what are electric field lines. So if this is one charge, if this is, let's say, a positive charge, I can draw the electric field lines, which basically defines how strong that charge is. So I can draw the electric field lines in the outward direction. So these are electric field lines for a positive charge. Same way, if there is a negative charge, I can draw the electric field lines around that particular charge, and these electric field lines will be negative. So how do I remember this thing? Is positive sun gives us energy, and we correlate sun with the positivity, so it gives you the energy, positive charge. So that's how I kind of remember always. And for negative charge, it sucks in all your energy. Now, if I'm going to place a positive charge and a negative charge together, so the electric field lines will start from the positive and move towards the negative charge. That's how they're going to move. And I can draw multiple electric field lines like this. Now, one thing you need to remember is that these electric field lines will never intersect. So what do I mean by that? Electric field line cannot start from here and gonna intersect the other line and then gonna insert or gonna go to the negative charge. So that never happens. And another thing I want to tell you about the electric field lines is that they are denser, closer to the closer to the charge itself, and then as you move away from the charge, they becomes less dense. So that can be shown down here. So if I draw the multiple electric field lines coming out of this section, so how many electrical field lines I can draw, and then if I take a section, so here I'm going to draw this section. Here in this section I can uh, have one, two, three, four electric field lines. Now, if I'm going to move this particular section down here, so this is pretty much the size of that section, and maximum I can have. Okay, I'm going to increase it to this. Maximum I can have 3 electrical field lines in this section. So electric field lines are denser near the electrical charges, and as you move away, electrical field lines are less dense. Now, the next thing we're going to talk about is the electric potential energy. Electric potential energy. So here, before I start the electric potential energy, I'll like to recall the concept of potential energy, simple potential energy. So if this object is placed on the ground, and now you wanted to place it on top of this cliff, this is a cliff, and you place it on here. Now, what kind of an energy is stored in this one? And the energy stored in this one is potential energy, and that is virtue of its height. And then I can calculate that energy as with the formula mgh. That is the potential energy, the mass of this object multiplied by the gravity and the height at which you are placing it. So similar sort of a concept we can use for the electric potential energy. So if this is a negative charge and this is a positive charge, what is the natural tendency of these two charges? The natural tendency of these two charges is they're going to stay closer to each other. So they're going to stick by each other. Now, if I wanted them to repel away from each other, or if I want them to move away from each other, to move them apart, I have to add certain amount of energy into it. So means I'm going to apply certain force. So if I apply, let's say, 10 Newton of force, and then that causes it to move to a certain distance, let's say of 1 meter, that will be formed in form of electric potential energy, EPE. So now the energy in this charge has been stored as the electric potential energy, assuming this is constant. So I'm going to say this is a stagnant charge. I move this charge towards the right hand side. So maybe 2 joules, maybe 3 joules amount of energy has been stored in this. Now, that was the case when you have the two charges which are opposite. Now, if I have the two charges which are exactly similar to each other, So the negative and negative charges, the natural tendency is to repel away from each other, to move away. Now, to move closer to each other, what do I need to do? I have to apply the energy to maybe to this charge or maybe to the other charge. In this case, I'm going to stagnate this charge, assuming this charge is fixed, and then I'm going to move this charge towards the other charge. So to bring them closer to each other, whatever energy I have to apply to the system, that will be stored in the system as electric potential energy. And electric potential energy is same as that of the work done on the system. And the formula for that will be force times the distance moved, but we don't need to get into that. At our level, we only need to equate it equal to the work done. So hopefully you were able to understand the concept of electric potential energy. And again, there are two units for the electric potential energy. One is the joules, another is electron volt. So what is the relation between the joules and electron volt? So 1 ev is equal to 1.6 times 10 raised to the power negative 19 joules. That is the relation. So if you are asked a question to find out the electrical potential energy stored in a system in form of ev, you will be able to do the conversion if the things are given to you in terms of joules. All right. Now, let's look into the next thing, that is electric potential. Electric potential. So what is electric potential? So the definition for the electric potential is electric potential energy, electric potential energy divided by charge. That is electric potential. Now I'm going to try and make you understand this with the help of diagram. Let's say this is a sphere which has 2 coulombs of charge onto it. Okay, I'm going to say positive 2 coulomb of charge onto it. I wanted to find out the electric potential. Now, one thing I will define here is this is a negative charge, and I moved this charge to a distance of 2 meters away from this, and I'm just taking a random number here. By moving this charge 2 meters away from a negative charge, the electric potential energy stored in the system is, let's say, 5 joules. Again, this is a random number I'm taking. Now, this charge is 2 coulomb, so electric potential will be equal to, electric potential will be equal to 5 divided by 2. That will be approximately 2.5. And the unit will be, unit for this will be joules per coulomb, because this is the unit for energy is joules and this is coulomb, so joules per coulomb. Or another unit for electric potential is volt. Okay, because he was the scientist who discovered, or he talked about this thing for the first time, so the unit are also volt for the electric potential. So hopefully you were able to understand what is electric potential, and the formula is energy EPE, electric potential energy divided by charge. That's the formula for volt. And now the next is electric potential difference. Electric potential difference. So electric potential difference is, as the name suggests, delta V, V final minus V initial. So I'll try to explain it with the help of a diagram. So if you see an electric socket, there are 2 holes in a electric socket. Now what happens, or plug-in, whatever you want to call it, I think it's a plug-in. So here the electric potential is in one of the holes, the electric potential is always bigger than compared to the other one. So I'm going to take some random numbers here. Let's say the volt here is 120 and at the other is 0. Because there is a difference between these two, one has electric potential of 120 volt, another has an electric potential of 0 volt. That's why the current flows in the circuit, or the electricity flows in the circuit. So when you're going to connect it with the wire, one wire takes out the voltage. Means first of all the circuit gets completed like this within the wire, and here down here, oops, I can attach a bulb here. Okay, let's say a resistance or a bulb. So these electrons flow from here with a very high voltage, and then they lose out their energy to this bulb, which comes out in the form of light energy, and these electrons start flowing back into the other hole. It's the same concept why the water flows. If there is a leveled floor and the water is spilled to the surface, then water will stay stagnant. But if I'm going to tilt it, then this is a higher voltage and this is the lower voltage, or maybe higher height and lower height, and the water will start flowing in the downward direction. And same concept can be applied to the electric potential difference. So because of the electric potential difference, you get the electricity in your house. So it is electric potential difference is denoted by formula delta V, which is equal to V final minus V initial. Now, this was the theory part of the chapter number 11.2. One of the formulas which I wanted to tell you for the electric field, E is equal to delta V upon divided by delta T, means change in the voltage divided by the displacement. And another formula for electric field is equal to KQ divided by R square. Remember the force formula? Force formula was KQ1 Q2 divided by R square. Now electric field formula is this one, and this is the formula you used in chapter 11.1 while talking about the electric field lines. Now electric field lines or electric field can also be represented by this formula. So if in a question you are not given the charge, you're not given the distance from a particular point, if and you are given the voltage, means electric potential difference is given to you and the displacement is given to you, still you can find the electric field. So based on that, I'm going to try and take a question, and that question is I'll take a question here from example 11.8. Example 11.8. Again, this is from the Alberta Pearson book, and it is on page 566. So a small charge of 3.2 times 10 raised to the power negative 19 coulomb moved between the two parallel plates. So I'm going to draw the diagram. So these are the two parallel plates. One is a negative, another one is a positive. So let's assume this positive charge moves from the positive end towards the negative end. At point A, it has a electric potential of 2.0 times 10 raised to power 3 volt, and at point B, it has an electric potential of 4.0 times 10 raised to the power 3 volt. I wanted to first of all find what is the difference in the electric potential between A and B. So delta V will be equal to V final minus V initial. You can always do this way also, V higher minus V lower. That will be that's going to make your life easier. Whatever is higher, that the lower one will be subtracted from the higher one. So 4.0 times 10 raised to the power 3 minus 2.0 times 10 raised to the power 3, that's going to give you 2 times 10 raised to the power 3 volt. That is the electric potential difference you figured out. Now, the next thing we're going to try and figure out is I wanted to find out the electric potential energy stored in the system. Electric potential energy. that'll be equal to delta V equal to delta EP divided by Q. So here, one thing, do you remember that formula V equal to E divided by Q I used? Means how much EPE divided by Q. So if I'm placing a delta here, I'll place a delta here. Means change in energy gonna give you change in the potential also divided by the total charge. So that's what I'm doing. Delta V equal to delta E divided by Q. Remember, when I'm talking about electric potential energy, I'm using this symbol for energy. When I'm talking about the electric field, I am using this symbol. This is electric field and this is electric potential energy. Now, if I were to do the math, this will be equal to, I'm trying to find the electric potential energy. Delta E is equal to this divided by charge, and electric potential difference is how much? 2 times 10 raised to the power 3. 2 times 10 raised to the power 3. And now what I can do is I can multiply 2 times 10 raised to the power 3 multiply by charge equal to delta E. I didn't tell you initially how much this charge was. This charge is 3.2 times 10 raised to the power negative 19 coulomb. So I can multiply this number 2 times 10 raised to the power 3 multiplied by 3.2 times 10 raised to the power negative 19. That's going to give you delta E. Now, if you were to convert, well, this value will, first of all, let me tell you how much this value will be. That value will be 6.4 times 10 raised to the power negative 16 joules. And now, if I were to convert it into EV, electron volt, EV in this format. So how can I convert it into that? 1 EV is equal to 1.6 times 10 raised to the power negative 19 joules. So I will write EV on top and joules on the bottom. So EV is 1.6 times 10 raised to the power negative 19 here. And I wanted to find EV. So EV is on top. So I'll put it as an X. And down here, 6.4 times 10 raised to the power negative 16. And then I'll cross multiply this on the other side. 6.4 times 10 raised to the power negative 16 divided by 1.6 times 10 raised to the power negative 19 equal to X, which is going to give me 4 EV, 4.0 electron volts. So hopefully you were able to understand this question. I still couldn't do the question on this formula, delta V equal to delta, well, actually not this formula. This formula I couldn't do the question on, this one, electric field lines. So that question you can do it from example 11.9. I'll leave it up to you guys. If you can solve it, you can always ask me, you can email me, I'll help you with that question also. So hopefully you are able to understand chapter 11.2. I'll see you with another video. Till then, goodbye.